Welcome to The Explainer. Today, we're taking a deep dive into the very heart of the machines powering our modern world. We're going to break down the anatomy of a computer, looking closely at its internal life cycle and that brilliant structural hierarchy making all this computing actually possible.
It kind of feels like science fiction, right? But the reality is pure, elegant engineering. How does a machine actually think? To truly understand a computer's brain, we can't just admire the sleek exterior. We've got to peel back the layers, zooming all the way in from the massive foundational blueprints right down to the microscopic memory cells holding individual bits of data.
Okay, let's dive right in. Here's our agenda for today. First up, the architectures of computing. Then, categorizing computer processors. Third, inside the CPU. Fourth, the memory hierarchy. And we'll wrap up with input, output, and storage.
All right, Section 1, the architectures of computing. You know, the entire computing world basically balances on two primary models. First, we have the von Neumann architecture, proposed by John von Neumann way back in 1945. The big takeaway here is that it uses the exact same shared memory to hold both your data and your instructions. Because they share that single path, one instruction actually takes 2 clock cycles. Then we have the Harvard architecture. This one uses completely distinct, separate physical memories for instructions and data, which lets it do 2 simultaneous memory fetches. So yeah, it's significantly faster, but as you'd guess, it's also more expensive to build.
The von Neumann setup brilliantly illustrates how the CPU and the memory share a single, common pathway for addresses and data. It's kind of like a single-lane highway. Because the CPU can't access instructions and perform read or write operations at the exact same time, you get a potential bottleneck. But hey, this shared approach keeps hardware costs way down, which is exactly why it's the go-to architecture for personal computers and smaller-scale devices.
Now contrast that with the Harvard architecture. Here you get separate, distinct physical pathways, one entirely for data memory and a completely different one for program memory. This is a real game changer because it means the CPU can fetch an instruction and perform a read or write operation at the exact same time. While it definitely costs more than the von Neumann model, this high-performance capability makes it absolutely perfect for specialized tech, like microcontrollers or digital signal processing devices used in things like radar and sonar.
Moving on to Section 2, categorizing computer processors.
To really make sense of how processors are organized, we rely heavily on Flynn's classification. Introduced by Michael Flynn, this taxonomy is pretty much the standard way we categorize systems, especially those doing parallel processing. It breaks everything down into 4 distinct streams based entirely on how instructions and data are handled.
First up is the Single Instruction, Single Data Stream, or SISD. In this setup, one instruction runs on one single processor, using data stored in a single memory. Machine instructions are executed in strict sequential order. Honestly, this represents most conventional uniprocessor computers. It's the classic sequential processing we all think of when we picture a standard computer executing a basic task.
Next is the Single Instruction Multiple Data Stream, SIMD. Here, a single machine instruction controls the simultaneous execution of multiple processing elements. Each processor has its own local memory to execute that exact same instruction, but on totally different sets of data. This architecture is absolutely perfect for scientific computing, vectors, and arrays. Imagine you've got a massive array of numbers, and you need to subtract the number 10 from every single element. Well, SIMD allows you to do that simultaneously across the whole board. Pretty cool, right?
Then we have the Multiple Instruction Single Data Stream, or MISD. In this model, a sequence of data is transmitted to a whole set of processors, but every single processor executes a different instruction on that exact same data. Think of calculating the sine, cosine, and tangent of the same variable at the exact same time. Now, while it's conceptually super fascinating, this specific architecture isn't really commercially implemented or highly useful in most standard applications.
Finally, there's the Multiple Instruction Multiple Data Stream, MIMD. Now, what's really interesting here is how these different processors take programs and data from a common shared memory and actually communicate with each other through that memory. This is the whole basis for modern symmetric multiprocessors, or SMPs, where multiple processors of similar capabilities share access to memory and I/O devices over the exact same buses.
All right, Section 3, inside the CPU.
Let's zoom right into the CPU itself. The arithmetic and logic unit, the ALU, is what handles all the actual math and logic. Now, CPU organization is really defined by where that ALU gets its operands from to perform those tasks. In a stack CPU, operations are only performed on data held in a stack. Simple enough.
In an accumulator CPU, the very first operand always has to be in a specific register, cleverly called an accumulator. And in a general register CPU, you're looking at a much more flexible architecture. Operands can be pulled register to memory or strictly register to register, just depending on how many registers the CPU actually has available.
Let's move to Section 4 and see how this builds, the memory hierarchy. To store all this information, the computer obviously needs to know exactly where it is. Let's look at the numbers. Say a system has a total memory of 128 gigabits, grouped into 16-bit words. We have to calculate the addressing space. Because memory is divided into individual cells, we absolutely need a unique binary address for each one. By applying some basic logarithmic math to that 128 gigabits, we find that to address every single bit individually, we'd need a 37-bit address. To address by byte, we'd need 34 bits. And to address by whole 16-bit words, we only need 33 bits. So knowing our memory locations and bit lengths is completely vital for uniquely addressing and retrieving your data.
But keep in mind, memory isn't just one flat landscape. It's a hierarchy, essentially a pyramid designed around three things: size, cost, and speed. At the very top, level 0, you have internal memory, those incredibly fast but super expensive and tiny registers and cache. Level 1 is your main memory, like RAM. As we move down the pyramid to level 2, secondary memory, like hard disks, and down to level 3, tertiary memory, like tape drives, the storage capacity gets massive and way cheaper, but it also gets significantly slower to access.
To navigate that pyramid efficiently, computers rely on the principle of locality of reference. So the crucial point here is that data you use frequently, or data clustered right near what you're currently working on, is temporarily kept in that smaller, faster cache memory. This principle is literally the entire secret to why cache memory so dramatically speeds up system throughput. It completely prevents the lightning-fast CPU from having to just sit there twiddling its thumbs, waiting for slower main memory to deliver the goods.
And finally, zooming back out, Section 5, Input, Output, and Storage.
So how does the computer talk to the outside world? We use peripheral devices, which connect externally to the CPU through a bus arrangement. They fall into three super straightforward categories. Input devices, like your keyboard, scanner, or webcam, they send data in. Output devices, like your monitor or printer, they display data out. And storage devices, like hard disk drives or flash drives, which handle all that secondary memory retention.
For secondary storage, things like magnetic hard disks, the physical organization is just a marvel of engineering. The disks contain platters with recording surfaces on both sides. To actually locate your data, the disk physically rotates. So your total access time is a combination of the time it takes the read arm to seek the track, the rotational latency waiting for the data to spin around, and the actual transfer time itself. To minimize that seek time while this thing is spinning at thousands of RPMs, data is logically formatted into cylinders. The system then locates exact data blocks using a very specific triple formatted address. It finds the correct cylinder, then the correct surface, and finally the exact sector.
So, what does all this mean for you? Look at the device you're using to view this explainer right now. Underneath that sleek glass and metal, which architecture is it running? Is it utilizing a specialized Harvard blueprint? How many address bits is its processor using to navigate its memory hierarchy? By understanding these foundational blueprints, you aren't just using a tool anymore. You're commanding a highly orchestrated symphony of logic. Keep questioning, keep investigating, and definitely enjoy exploring the anatomy of the tech right there in your own hands.